Hello everyone, I am Suvrat and today we'll be discussing CodeChef Starters 215. Let's start the discussion. Problem A. Special missions. You are playing a game with n missions to complete. The ith mission pays AI coins. You can choose whether to complete each mission or not and also the order in which you want to complete them. However, some of the missions are special ones and to access them you need to pay a one-time fee to a wizard of C coins. You only need to pay once, not per every special mission you wish to complete. You are also given a binary string S where Si is equal to 1 if the ith mission is special and Si equal to 0 otherwise. What is the maximum coins you can obtain? You start with 0 coins. Note that you cannot have a negative coin balance at any point of time. That is, if you decide to pay C coins to the wizard to unlock the special missions, you must have at least C coins with you beforehand. And the constraints are 100 test cases, n is less than equal to 100, so expected time complexity would be around O of n square. So problem A, basically we are given n missions and each mission gives AI coins, and C coin fees to unlock the special missions. We need to find the maximum coins that we can obtain. So let's see the test cases. The first test case is C equal to 2 and A is 1 5, and this is a normal mission and this is a special mission 0 1. So basically, since we need 2 coins to access the special missions, we will need to first earn minimum 2 coins, then only we can access the special missions. So since there is only one normal mission which does not require which does not require a C fees, so we will complete this mission and then we will not be able to complete this mission since we cannot pay a fee of 2 coins since we only have 1 coin. So answer will be 1 for this test case. The next test case is 2215, and but now this is a special mission and this is a normal mission and C is 2 again. So here we can first complete this mission, then we will have a 5 coins, then we can either choose to give a fees of 2 and complete the special mission, or we can choose to skip all the special missions and then we won't have to pay the C fees. So it is obvious since the fees is of 2 and we will be only earning 1 coin after we pay that, so that is a loss for us, so we'll not be doing that. So the answer for this test case will be 5 only. But if had we paid the C coins and accessed the special missions, then the final coins would be 4. That is less than 5, so we would avoid that. Then the next test case is 10 10 10 10 0 0 1 1 and C is 5. So C is 5, A is 10 10 10 10, normal, special. So now obviously we can see that there are 20 coins worth of special missions and 20 coins worth of normal mission. So obviously we will complete all the normal missions and then we will obviously pay the fees of 5 coins to access the special missions since we'll be getting 20 coins by doing the special missions. So we'll do 20 minus 5, which is 35. So 35. Then the next test case, both the missions are special and hence we will not be able to pay the 1 coin fee. So we cannot, there is no mission that we can do. So answer is 0. And then again here, we will first complete the normal missions, which are 3 3. That will give us 6 coins, and then we will buy the special missions by using these 6 coins and complete the special missions, which is of 100 coin. So answer will be 100. So basically, the key observations are, one of them is we will complete all the normal missions in any case. And then a second observation about the special cases is that we will buy we will unlock the special missions actually, only when c is less than equal to, actually c is strictly less than sum of all ai, such that si is equal to 1. Basically, sum of coins for all special missions. So we will only pay the fees of C coins if we know that we will be earning more than C coins after we pay the fees of C coins. Only then we will. So the two cases, uh, if C is less than special, then the answer is just normal. Else, okay, actually we can do it like this. If normal is greater than or equal to C and C is less than special, when these two conditions are met, only then we will buy the access to the special missions. And in this case, the answer would be normal plus special minus C. Else, the answer would just be normal. So we will need to find the sum of normal coins and sum of special coins. That will require an iteration over the array. So in O of n, we can do that. And this is an O of 1 output. So the total time complexity would be O of n. I'll show you guys the code. So you can see the code here. First I take input the test cases, the n and c, and then the vector v and the string s, and then I calculate the normal and special sums. So if si is equal to 0, I add it to the normal. If si is 1, I add it to the special. And if normal is greater than equal to c and special is greater than equal to c, only then normal plus special minus c, else only normal. So that was the solution for problem A. If you guys have any doubts, you can ask. Okay, so I don't think you guys have any doubts. So let's move on to the next problem. So this problem is differing values. You are given a binary string s of size n and a parameter k. You are wondering whether it is possible to rearrange the characters in s such that the following conditions is satisfied. Si is not equal to si plus k for all 1 is less than equal to I less than equal to n minus k. Print yes if it is possible to rearrange s in such a way and no otherwise. And the constraints for this problem is t is less than equal to 100 and n and k are also less than equal to 100. So expected time complexity would be of the order O of n square or O of n into k, something like that. Problem B. So basically we are given a string, binary string s, we can rearrange string to meet the following condition, which is that si is not equal to si plus k, where k is given in the problem and I is less than equal to n minus k. And we need to tell if we can rearrange such that this condition is followed for every I or not. So let's see the test cases. The first test case is 4 1 1 0 1 0. So 4 n equal to 4, k equal to 1, s equal to 1 0 1 0. So first things first, since we can rearrange, so the string doesn't really matter. The only thing that matters is the count of ones, which are 2, and counts of zeros, which are also 2. Since we can rearrange, this is the only important thing. We don't really care what initial string we were given. We can rearrange it into any string, right? So ones are 2 and zeros are 2. Now we are given that k is equal to 1. So what conditions do we need to satisfy? We need to satisfy that s1 is not equal to s2, s2 is not equal to s3, s3 is not equal to s4. That's it. So we need to satisfy these three conditions, right? So s1 is not equal to s2 and s2 is not equal to s3. So that must mean that if s1 is 0, then s2 will be 0. If s1 is 1, then s2 will be 0. And since if s2 is 0, then s3 will be 1. And if s3 is 1, then s4 will be 0. So what we can say is basically s1, s3 are equal and s2 and s4 are equal. Basically alternate. We have this sequence, right? S1, S2, S3 and S4. So S1 is not equal to S2, S2 is not equal to S3, S3 is not equal to S4, like that, right? So what we can say is S1 is equal to S3 and S2 is equal to S4. Since these two are not equal and these two are not equal, so these two must be equal. Since S1 and S2, S is a binary string, it can only be 0 or 1. So if these two are not equal and these two are not equal, these two must be equal. So like that, we can say that S1 and S3 are equal and S2 and S4 are equal. So what we can do is we can either make S1 and S3 as 0 and S2 and S4 as 1. That would be one solution to this problem, which is 0, 1, 0, 1. And another solution would be S3 and S1 would be 1 and S2 and S4 would be 0. That would be 1, 0, 1, 0. So these two possible strings are there that can make these conditions true. So the answer for this is yes. Now the next test case. So the next test case is 431001. N is equal to 4, k is equal to 3 and s is equal to 1001. So again ones would be 2 and zeros would be 2. And the condition that we need to follow is s1 not equal to s4. That's it, only one condition. So now this is a pretty easy test case. We can just do 1 0 0, actually 1 1 0 0, or we can do 1 0 1 0, or we could have done 0 1 0 1 0 0 1 1. So we just need to ensure that the first and last are not equal. That's it. So obviously we can do that. Hence the answer for this test case is also yes. Then again the next test case is 4 1 1 1 1 1. So since n equal to 4, k equal to 1 and s is 1 1 1 1. So the condition again, the important thing is zeros are 0 and ones are 1. And the conditions we need to follow is s1 not equal to s2, s2 not equal to s3, s3 not equal to s4. So yep, we will not be able to do this since the only numbers we have are ones, and if we the only string that we can make will be this, and we cannot ensure these conditions. So the answer for this test case is no. And then the last test case is 4 to 1110. So n equal to 4, k equal to 2, and s equal to 1110. So zeros equal to 1, ones equal to 3, and the condition that we need to follow are s1 not equal to s3, s2 not equal to s4. That's it. So we just need to again, if we put s1 as 1, then s3 will be 0, and if we put s2 as 1, then s4 will be 0. Or if we had done this, basically either way, the number of ones and number of zeros used will be the same, right? We can see that. So that means that we won't be able to do this since we have only 1 0, right? So we can only make one of these pairs. We can either satisfy this condition or we can satisfy this condition. Both of them we will not be able to satisfy. So the answer is no. We would need 2 zeros and 2 ones to actually make a possible string. So we didn't really learn much from the problem, from the test cases, but we can make observations from this test case that we did solve, where we saw this pattern coming up. So what actually is this pattern? Let's analyze. So we had this condition given that si is not equal to si plus k, where I is from 1 till n minus k. So basically this condition can be seen as this: si is not equal to si plus k, which is again not equal to si plus 2k, and which is again not equal to si plus 3k, and which is again not equal to si plus 4k, and so on it will go. So basically for now, let's just imagine that I plus 4k actually this is nothing but this condition is nothing but we are just putting I as I plus k. In this equation we are just putting I as I plus k, so we get this condition, and we get this condition, and we get this condition basically. So also let's just assume that this index is currently less than equal to n only. So let's assume that I plus 4k is less than equal to n. So we can do this. So what this will tell is that these two are opposite to each other and these two are opposite to each other. So basically these two must be equal to each other, and these two must be equal to each other, and again these two must be equal to each other. So basically we are seeing that to satisfy this condition, we need either 3 ones and 2 zeros, or 2 ones and 3 zeros. Basically we need to make these three same and these two same. So we need 2 zeros and 3 ones, or 3 zeros and 2 ones. So we need either of these to satisfy all these conditions, and then we will get the same corresponding case corresponding to I plus 1. Basically I plus 1 will not be equal to I plus k plus 1, which will not be equal to si plus 2k plus 1, and so on. And again I get conditions like this. So in these conditions there will only be two cases: when this sequence is of even length and when this sequence is of odd length. We saw that in our test case the sequence was of even length. So in even length we saw that the number of zeros and number of ones were equal. So if even number of zeros is equal to number of ones, and if odd, basically either number of zeros equal to number of ones plus 1 or number of ones equal to number of zeros plus 1. So basically we need one extra 0 or one extra 1 to solve the odd case, and like that. So now let's take an example of n equal to 10 and k equal to 2, k equal to 3 and n equal to 10 is fine, I guess. So here we will have the conditions s1 not equal to s4, which is not equal to s7, which is not equal to s10, and s2 is not equal to s5, which is not equal to s8, and s3 which is not equal to s6, which is not equal to s9. So these three sequences of condition that we need to satisfy. So first is of odd length, right? So according to this, we need 2 zeros and 2 ones. And now the next sequence is of odd length. First is of even length, next is of odd length. So odd length, we need minimum of 1 0 and 1 1 number. So let's do it like this: zeros, ones. So 2 2, and we need a minimum of 1 1 and again 1 1, and then we need an extra 0 here or an extra 1, and same for this, an extra 0 or an extra 1. So basically we need minimum 4 zeros and 4 ones to solve this test case, and then whatever zeros and ones we have left, we can put it in one in this sequence and one in this sequence, and we will use them all. So we need minimum of 4 zeros and 4 ones to solve a test case like this. So similarly, to solve the question, what we can do is we can first identify the sequences, and then we can count the number of zeros and ones that we that we have to have. Basically here we have to have 2 zeros and 2 ones, 1 0 and 1 1, and 1 0 and 1 1 again. So we have to have a total of 4 zeros and 4 ones. Anything less than this, we won't be able to make this sequence. So we have to have 4 zeros and 4 ones. And now let's take the case where we had 4 0 and 5 6 ones. So in this case, what we will do? We will do 1 1 0 0 to satisfy the first sequence. Then since we have extra ones, what we will do? We'll put 1 1 like this and 0 here, and again 1 1 like this and 0 here. Or if we had 5 0 and 5 ones, what we would have done is we would have changed this to 0 1 0. So you can count 1 2 3 4 5, 1 2 3 4 5. So we can satisfy in any case. We just need to ensure that we have a minimum these many zeros and ones. So what we can do is we can just count this number of zeros and number of ones required in each sequence, and then add all them to find the minimum number of zeros and minimum number of ones required. So we can do this in O of n, and I'll show you guys the code. So first we take input n and k, then we take input string s, then this we count the number of ones and number of zeros, and then basically what I'm doing is I'm maintaining a vector v which will keep track of these sequences, vector of pair v which will keep track of these sequences. So what I will do is from I1 till In, if visited of I, then I'll continue, else I will just do this. I'll set current to I, and then I will run a while loop, current plus k is less than equal to n, and just add k to current and visit every number that I am marking, that I am visiting in the sequence. And what I can do is I can count the number of zeros and ones by maintaining a array which will count me the zeros and ones. So basically I will alternate. First I will add the first number to val which is initially 0. So first number will be added to type 0, and then in each iteration I will be changing the value of val. So in the second iteration, then type of 1 will increase. In the third iteration, type of 0 will increase, then type of 1, then type of 0. So basically I will alternate between 0 and 1, and then in the end for the whole sequence I will push it back in the vector v, and then simply I will count the number of zeros and ones required. So if I dot first is equal to I dot second in vector v, then that means that was an even sequence, so I can just subtract it from the 0 and 1. Else what I will do, I will subtract the minimum of I dot first and I dot second from 0 and 1, and this will be an odd, because this was an odd sequence, so I can either use the extra 0 or the extra 1. Basically I just need to have the minimum of both in zeros and ones, and then in the end if left out zeros were greater than 0 and left out ones were greater than 0 and the number of left zeros and ones are greater than count, this will actually be always true. But yeah, you can add that as a condition as well, and then see out yes and else see out no. So that was the solution for problem C. Why CNT1 greater than equal to index CNT and CNT0 greater than equal to IDX CNT, where IDX CNT is number of indices I plus K less than N. Do you still have that doubt, Ishan? This will if you guys have any doubts, you can ask. I don't get the part how you maintain. Okay, so let's go through it line by line. So basically, for each sequence, one thing you could have done is, what I could have done is simply I plus tk is less than equal to n, and then tk is less than equal to n minus I. This is one based, this is one based, right? My code is for zeros, and then I will get the t as n minus I is less than equal to k. This is probably the better approach. So I'll just get the t for each sequence in O of 1. But I just decided to go with this. So basically what I'm doing is, I have a sequence like this 1 2 3 4 5 6. I have an array like this 8 9, let's take till 9, and let's say that k is equal to 3. So what I'm doing is, I am maintaining a visited array which is initially all zeros, and then what I'll do, I'll come to the first index. I see that it is not visited, so I'll mark it as visited, and then I will go to I plus 3, which is 4, and mark this as visited, and then I'll go to I plus 4 plus 3, which is 7, and mark this as visited, and then I cannot go further. And while I'm visiting, what I'll do is, initially my count will be 0 0. Here I'll do my count as 1 0. Here I'll do my count as 1 1. Basically on every alternate turn, I will first add this one, then I will add this one, and if there was another, then I would have added this one. So basically this is the type array. So I'll just, so in the end I will know that this sequence had 1 1 and 1 0, and then I'll come to the second index and I will see that it is not visited. So again I'll do the same. I'll visit this, then I'll visit this, and then I'll visit this, and so my array will also look like 0 0, then 1 0, then 1 1. For 3 also I'll do this, I'll mark them visited, and my array will look like 0 0, then 1 0, and then 1 1. So my sequences ended at 7 8 and 9, right? So the vector v would look something like this: 1 1 1 1 and 1 1. Let's say if we had 10 also, so this 7 would have extended to this 10, and the sequence here would have become 2 1, and instead of the sequence ending at 7, it would have ended at 10. So it would have been 2 1 in the vector v. So the vector v would have looked like this. And now what I'll do is there should be at least 1 0 and 1 1 from this, 1 0 and 1 1 from this, and 1 0 and 1 1 from this. So I will just subtract them and just check if the end product is greater than equal to 0 or not. So that's what I'm doing. I don't get the part how you maintain odd sequence. So here the sequence was odd, right? So it would have been come out to be 2 comma 1. So in the code, what I did was I only subtracted the minimum of 2 and 1 from the value from 0 and 1. I only subtracted the minimum of both. So that way, since the necessary number of zeros and ones are only the minimum of I dot first and I dot second. Did you get it now? Or you can just do this. Doing this is probably better. So for every I, you will just get the number of terms in its sequence. And I here would be from 1 to k minus k, because k plus 1 is just a part of this sequence, right? So every term after k plus 1 would be already counted in the sequences before that. So from I1 to k, you can just know the number of terms in that sequence. And t by 2 will be the minimum number of zeros and ones. Okay. Bro, I have a theory for solving this, but I have exam tomorrow and so didn't solve it further. So hear me out. Yes, t equal to n minus I upon k is good. Okay, tell me. As we know, the window size is k. So if you want the condition to be followed, the next k element should be complement of that, right? Okay, so basically you are saying that since the window size of k, so these are k elements. The next k elements are, if these are a, this would be not a. Yes, that is correct. This string and this string should be complement of each other. That is right. Then for example 1010, then the next 4 elements should be 0101. Count all zeros and ones and check. But you would have to fix one of the. How do you determine what are these elements? How are you fixing them? Can you once take this example and explain, bro? 00011 k equal to 2. So 00011 k equal to 2. So according to k equal to 2, we have S1 not equal to S3, which is not equal to S5, and we have 1 2 3 4 5 elements. So that's it. And S2 is not equal to S4. So these two conditions we have. Then from this we get to know that there should be minimum 1 0 and 1 1, and again for this also there should be 1 0 and 1 1. So there should be a minimum of 2 zeros and 2 ones. So what we can do is, since we have 3 zeros and 2 ones, we will be able to make the, we will be able to rearrange the elements. So since these two must be equal, so we will put 1 1 here and 0 0 here and 1, and these two are unequal, so we'll do 0 1. So the answer is 0 0 1 1 0. So S1 is not equal to S3, which is not equal to S5, and S2 is not equal to S4. So that's how you'll get Spartan. Do you understand? Here, because it is odd, so we would have the liberty of choosing one element whatever we want. Your approach, basically I can try, but I won't waste a lot of time. We need to move on, right? So one thing you can do is you can, let's say that here there are O zeros and O is not a good variable. So T0 zeros and T1 ones in this first k elements. Then we can say that here there would be T0 zeros and ones. So here would be ones and T1 zeros. But the problem is your array won't be a multiple of k, right? And also your array won't be a multiple of k, so the remaining elements would cause you some trouble. So that is a problem because you don't have particular information about this part. So we would have to store two things. First this T0 and T1, and then out of these T0 and T1s, how many zeros are and ones are there in this part. You would have to store this. So you will have four variables, T0, T1, and then X0, X1. And according to these X0, X1, you will get the count of zeros and ones in this part. And now you will have the information about every part and you just add them. So sum of all the zeros should be less than total number of zeros, and sum of all the ones should be less than total number of ones. Actually equal. So you need to find whether there exist four variables T0, T1 and X0, X1 that satisfy these two conditions, and then you will know that there is an answer. And other two conditions that we have are X0 would be less than equal to T0 and X1 will also be less than equal to T1, and X0 plus X1 would be equal to this. Let's say that there are P elements here, so would be equal to P, and T0 plus T1 would be equal to K. All these equations you need to do. So yes, probably they will be, you will be able to solve because X0 and T0 would be eliminated from this, and then only for two variables you need to check this. So yep, you would get a solution. Thank you. So mini will be len of chain by 2. Yep. That is right. So Scooby Gamer. So you understood, right, what we can do? We'll need to maintain these four variables at first, and then I can probably take some example. I don't think this would be too hard. Do you want? Okay. So it's fine, right? So I think let's now move on to the next problem. So the next problem is product sum arrays, easy version. This is the easy version of the problem. Here you need to print a minimum of r comma 3 instead of r itself. You are given an integer n, and array A is called good if it satisfies all of the following conditions. So if 1 is less than equal to ai less than equal to n, ai less than equal to ai plus 1, and a1 plus a2 till a of length a is n, and a1 plus a2 till a of length a is n, into multiplication and addition of the whole array would be equal to n. In the array, in other words, the array should consist of non-decreasing positive integers, and its product and sum both must be n. So we need to count the number of such arrays and actually tell the minimum of r and 3. So problem C, we are given n, and for a given number n, we need to count r is equal to count of number of arrays which are non-decreasing, which is nothing but ai is less than equal to ai plus 1, and the sum and product are both equal to n. And we need to find minimum of r comma 3. So basically minimum of r comma 3 corresponds to just us wanting to know about 4 cases: r is equal to 0, r is equal to 1, r is equal to 2, or r is greater than equal to 3. So we need to know about these 4 cases. And first, now let's see the test cases. So the first is n equal to 1. So for n equal to 1, we can see that we have a corresponding array A, which is nothing but just 1. So the sum of this array is also 1 and product of this array is also 1. So there is no other array possible. So R is equal to 1. Answer is equal to 1 for this test case. So one thing we can say directly is that R can never be 0, because A is equal to n is always a possible array. Right, A is equal to n is always possible. That's always possible. So basically now we have cut down this case as well, and we just need to know about these 3. So the next test case, we have n equal to 2. Again, for n equal to 2, the only array is A is equal to 2. So answer is again 1. Then n equal to 3. The only array is 3. Answer is equal to 3. Then n equal to 4. Now we have one array A is equal to 4. The other that we have is A is equal to 2. Because 2 plus 2 is also 4. 2 into 2 is also 4. So the answer for this is 2. Then we have 5. A is equal to 5. Only one array. So answer is equal to 1. So you can see that these numbers are prime, right? These numbers are prime. So there cannot be anything. We cannot multiply two numbers and get this number, right? We can only multiply once and the number itself. So one more thing we can say that is, if n is prime, we know that the array must always look like 1, 1, 1, 1, 1 and n. And since this, because of the multiplication property, due to multiplication property, the array must always look like this. And since the sum is also equal to n, so we can't actually have these ones. So if n is prime, the only array possible is A is equal to n. So answer is always 1 due to addition. So if n is prime, the answer is always 1. So that's one observation we can make. Then the next is 6, n equal to 6, which is not a prime number. So one is A is equal to 6 is possible. Then what else? We know that 6 is 3 into 2, right? 3 into 2. Okay, A should be increasing. 3 into 2. But we know that the sum of these two is not equal to 6. The sum is only coming till 5. So what we can do is we can add another 1 and make this 1, 2, 3. Now the sum is 6 and the multiplication is 6. And since 6 has only one factor, 2 into 3, so there won't be any other arrays that we can make. So the answer for this will be 2. 7, again 7 is prime. So answer is 1. Then 8. For 8, what we can do is A is equal to 8 is one array. A is equal to 2, then 4. And these come out, these add up to 6. So we will have to add 2 ones. So 1, 1, 2, 4, which is 8. and another is 2 2 2. So this is 6, and then we'll have to add further 2's, 2 ones. So 1 2 3 4 5 6 7 8. So these 3. So answer is 3. We don't need to make any further because we already got 3, and this belongs to the case where r is greater than or equal to 3. So basically, we just need to find the number of ways to write a as a multiplication of 2 or more numbers. That's the entire question. We can see that we saw that 8 can be written as 8, or 8 can be written as 2 into 4, or 8 could have been written as 2 into 2 into 2, and then rest of the elements we can just add ones to make the sum equal to 8. For multiplication, we just need to figure out how in different ways we can write the number. Then again, in the test case n equal to 9, we have 9, we have 3 into 3, 6, which is 1 1 1 3 3. So only these two, so answer is 2. Then for 10, we have 10, we have 5 2 and 1 1 1. So that's it. So basically, now we can tell the solution pretty much. So if n is prime, then answer is 1, right? So what this can be written as is that there are no divisors other than 1 and n. So if that's the case, then n is prime, and the answer is 1. So now let's say that there is one other divisor other than 1 and n. So divisor equal to 1 comma n and some x. Then obviously the number will actually be just x into x, right? In any other case, there would have been more divisors. So in this case, we will have this array and we will have this array. So the answer for this case would be 2. So if there is one more divisor other than 1 and n, then the answer is 2. Now let's say there are two divisors other than n. So one array would be n and one array would be xy. Then we saw that basically because if these two are two divisors of n, then that must mean that x into y is equal to n. Only these two divisors will exist. Otherwise, we would have had more divisors. If x into y was not equal to n, let's say that x into y is not equal to n, then basically x into some x dash would have been equal to n, right? And this x dash would be n by x, which is not equal to y. So this x dash would have also been a divisor. So this y is actually, so x into y would actually need to be equal to n. Only then we would have two distinct divisors other than 1 and n. So x comma y would make one array, and one more case would be there, which we saw in the case of n equal to 8, where we had this extra case. So this extra case will only come up when this number is 2 into 2. So basically, let's say that out of x and y is greater than x. So we would have another if y is equal to x into x, then we will have this possible array as well, x, x, x. First case there will be 2, and in the second case there will be 3. And if divisor are 1 and some x, y, and z and more than these, so now we will have probably always more than or greater than equal to 3, always, because they must look like this. Actually, the order would be x will be less than z will be less than y. They will look like this. So in cases where other than 1 and n we have more than 3 divisors, so answer here would always be 3. So we just broke down our problem into specific cases and found the answers. So the problem boils down to finding the divisors, and since the constraints in the problem, we have n less than equal to 1e9. So we need to find the divisors in complexity better than O of n. So what we can do is we have a algorithm to find the divisors in O of square root n, which is simply I is equal to 2 I into I less than equal to n and I plus plus. And now we will have two divisors in each iteration, I and n by I. And we would need to handle the case where I into I is equal to n, because there I and n by I would be equal. So we can just handle this case separately. And this square root and for loop will give us all the divisors. And then we can just, if n is prime, that means there came out to be no divisors, then the answer is 1. If there came out to be one divisor, then the answer is 2. If there came out to be two divisors, the answer is 2 if this, and if y is also equal to x into x, then the answer will be 3. And if there are more than 3 divisors, then the answer is great. Answer is 3. So these cases we can use to solve. I'll show you guys the code. So first of all, I take input n, then I find the divisors. This is the case where I into I is equal to n, and then I sort the divisor vector. And size is number of divisors. So if number of divisor came out to be 0, then answer is 1. If it came out to be 1, then answer is 2. If it came out to be greater than equal to 3, then the answer is 3. And if the divisors are 2, then we need to check for one condition. If y is equal to x into x, then answer is 3, else answer is 2. So this was the solution for problem C. If you guys have any doubts, you can ask. Can you explain this problem hard version, please? I would actually not be discussing that in this discussion, but I had solved that in the contest. And what you need to do is basically similar to this exact problem. Now the thing is, you just need to count the, I won't be explaining the whole process, but I'll just give you an overview. You just need to count the different AI greater than equal to 2. You need to solve this problem. Basically, this is what you need to solve. You need to find the number of different arrays A which multiply to n, and each term in A is greater than equal to 2, because the sum we can just adjust by adding more ones. So you need to solve this problem, which I used a DP to solve. So DP of current multiplication that I need, and basically I won't be discussing that. You can check my submission. You'll get it on my ID. You can check my submission. So if you guys have any problem in problem C, you can ask. I'll be discussing till E. Okay, so I don't think you guys have any doubts. Let's move on to the next problem. So the next problem is intersecting intervals. This is the easy version of the problem. Here there are no queries. Given two arrays A and B, both of length n, define f of a comma b as follows. Choose two intervals L1 R1 L2 R2 such that L1 and L1 union intersection of L1 R1 and L2 R2 is not empty, that is they share at least one point. The score of this choice of intervals is defined as sum of A plus sum of B, and f of L comma R is defined as the maximum possible score under the above constraints. Less formally, you have to choose intersecting subarrays from A and B and maximize the total sum of the subarrays. So you are given two arrays A and B of length n, find f of a comma b, and that's it. So, and the constraints for this problem is n is less than equal to 2e phi, and a b can be from minus 1e9 till 1e9, and the sum of n over all test cases does not exceed 2e phi. So expected time complexity looking at this would be O of n or O of n log n, because the sum of n is still 2e5, right? So problem D. So basically, let's follow the less formal definition. I find that more comfortable. So what we can do, what we need to do is take two intersecting subarrays from A and B, and find the maximum sum of both the subarrays. So what we need to do is, we are given two subarrays A and B like this, and what we can do is we can take this subarray in A and this subarray in B, and the thing is both of them should be intersecting, and then we need to sum of these elements and we need sum of these elements, and we need to add these sums and find the maximum value that we can get, basically like this. So intersecting subarrays could look like, I'll give you the examples. They could look like this, or they could look like this, or they could look like this. So these will be the three types of intersecting subarrays that we can have. So, and also like this. So yeah. Let's see the test cases now. These can be the intersecting subarrays. So the first test case is 1, 3, -1 and -1, 3, 1. So we can see pretty easily that choosing these subarrays is quite good, because now we had basically selected every single positive integer. So the answer will be 1 plus 3 plus 3 plus 1, which is 8. Then the next test case is 2, -1, -1, 2. 2, -1 and -1, 2. So here we can select this and this, or we could have selected this and this. That is just the symmetrical case. So we'll just select this and this, and the answer is 2 -1 plus 2, so 3. And then the next is -5, -10, -4, -5, -10, -4, -3, -2, -5, -3, -2, -5. So here literally every single element is negative. So the answer would be, since we need to select a subarray that is intersecting, so we just select these two, this only, this and this. So answer is nothing but -5, -3, -8. 1, 2, 3, 3, 2, 1. 1, 2, 3, 3, 2, 1. And since every single element is positive, we can just take them all, and the answer would be 1 plus 3 plus 2 plus 2 plus 3 plus 1, which is 6 plus 6, 12. Then the last is 10 minus 8 minus 2, 6. 10 minus 8 minus 2, 6. Minus 2, 3 minus 5, 7. Minus 2, 3 minus 5, 7. So what can we do here? We can take this 10 and but then let's avoid taking this -8 and let's take these 4 elements here. So what will be 10 minus 2 plus 3 minus 5 plus 7? What is this? 8, 11, 11 and 2, 13. Is it correct? Yep. So we can solve this test case like this. So basically we didn't learn much about the problems, and since what did we actually learn from this test case is that we couldn't do any greedy observations. We actually weren't able to do any observations at all. We just we had to use our instincts to solve each problem. Like for example, here every single element was a negative, so we just took the pair of elements which the sum was maximum. Here we took this -1 so that we can get this 2, and here we just selected all the positive. Here everything was positive. Here we didn't want to take this -8, but we had to take this 10. So like this, we didn't find any concrete observations that we could follow to solve the problem. So no concrete observations. And we also know one more thing. We know that max subarray sum is solved using DP. The max subarray sum problem for one single array, we know that it is solved using DP. So since there weren't really any greedy observations or any observations in particular, so we can kind of make an assumption that the solution would be around DP, and we can start from there, because generally in problems where we don't make any concrete observation, so those problems mostly require brute forcing, and brute forcing is DP. So let's try to build up our solution based upon DP. So what cases do we have? So we need, the problem says that we need to find two subarrays that must overlap with each other, right? So let's take a very simple case where the subarrays look like this, simply like this. Now we have 4 different regions, these 4 regions. So actually not 4, 1, 2, 3, 4, 5 regions. So let's just give them numbers so that we can talk about them comfortably. So let's just give this region 0, region 1, region 2, region 3, region 4. So we have 5 regions, and the answer is sum of A in region 1 plus sum of A plus sum of B in region 2 plus sum of B in region 3 plus sum of 4 plus actually that's it. So the answer is this, and we need to maximize over this, right? So what we can do is since we have 4 different possible regions, right, 4 different areas that we could be in. So let's define our DP based upon these 4 areas. So let's define our DP as I comma region, which will tell us this DP will store the answer for starting at the ith index and specifying that till now we were in this number of region, we were in this region, whatever this state has the value, we were in that region till now. Up till now we were in this region, and we need to find the answer from I till n, so that our DP will store. So according to this, DP of 0, 0 will be our final answer, because from 0 till n and in 0 region, starting from 0 region will be our answer, right? And the base case would be when I is equal to, let's just say that we are doing in 0 base. So this is 0 till n minus 1, this is I till n minus 1. So when I is equal to n, then that means that we don't have any other array left and we ended with this region. So since we are said that the array must overlap, right? So we cannot end before entering into region 2. We cannot end at region 1. So if region is greater than equal to 2, then we can simply return a normal value of 0. And if we didn't reach till region 2, then we can return a very undefined value of -1e17, which is a very small value. So that means that this state is not possible and we should not account this for an answer. So this was the overview of the DP, that the state would look like this, that this will be our answer and this will be our terminating base case and answer and state. The most important thing in our DP, the most important thing is now left, which is the transitions. So how do we transition? So we have 5 different cases that we need to write the transition for. Also, when we consider this case, we are actually forgetting that the case also might look like this, or it might look like this. These cases we can just account for in this only. These cases where they both end at the same index or they both start from the same index, we will be able to account in this only. But this case we need to handle separately, where this is completely inside this, because here we can see that our regions don't quite follow the same rule. We have 0 region, then we have 1 region, then we have 2 region. That is according to our case that we took. But then we don't have the 3 region. We now have a very different region where we are not adding the elements in B, we are adding the elements in A. So we need to actually account for this also, and we can mark this as region 5. So what we can do is, after ending the region 2, we can either go into region 5 or we can go into region 3. And after that, again, region 4 only. So this case we will need to handle separately. And if we had cases like this, I can say that they follow this pattern only, since we have region 0, then region 1, then region 2, and then we go to region 4. So basically 3 region is not there. So that means this, and then this, which is totally fine. But this was an exception case because this had a different region in between. We were not skipping out on region, but we are adding a completely different region in between. So we need to handle this separately. So we can handle this by defining this region as 5. And for this case, where the overlap is first, actually not this, I made the same thing over this case I'm talking, where the B array, the subarray is beginning in the B array and then the overlap is happening. So for this case, what we can do is, the exact same logic that we applied in this, we can just reverse the arrays A and B and then again apply the same code, and the 2 answers we get, we can just take the minimum of 2 answers. So this case is solved. We can just swap A and B and rerun the code. So that's it. And for this, we introduced a new region. Now let's try to define the transition. So first, let's analyze dp of I, 0. So basically, I is not necessary in the transitions. Only this number is necessary, the region. So what does this mean? This is this case where we are finding the answer from I till n-1, and previously we were in region 0. So what we can do is we can either continue in region 0. So one transition would be simply dp of I plus 1, 0, which is from I plus 1 till n-1, and we just continued the region 0. Or what we can do is we can go from region 0 to region 1. So that will mean ai plus dp I plus 1, 1. So now we have ended the region 0 and entered into region 1. So it will look like this. Region 0 was still here, then region 1, and then we are finding the answer from I plus 1 till n minus 1. So we can do it like this either. Or one more transition that we can make is AI plus BI, and we can go straight to region 2. We can skip out on region 1 and go straight to region 2, which is the case where the arrays might look like this. The arrays might look like this, A and B, the subarrays. So they might start at the same position. So we can actually start from the region 2 as well. So there will be these three transitions from dp I comma 0, and we can just take the maximum of them, which will be the perfect answer of I comma 0. The other case, now the next state is I comma 1. So that means that we had I till n minus 1, and previously we were in region 1. So since we were in region 1, one case is we can just continue to be in region 1. Or what we can do, we can enter region 2. That's it. We can either continue in region 1 or we can enter region 2. We cannot skip out on region 2 because we need the arrays to be overlapping. But if we skip out on region 2, then the arrays were not overlapping. Hence, that is not the case that we were asked for in the question. So only these two transitions here. So maximum of these two. Now let's find for dp I comma 2. So we can either continue in the region 2, or what we can do, we can end the region 2 and go into region 3. Or we can go into region 5. So either after region 2 we can come here, or after region 2 we can come here. So the arrays might look like this, or the arrays might look like this. Then dp I comma 3, we have simply 2. One is just continuing in this region, or another is ending this region and basically going into the fourth region. And I comma 5 also we have pretty much same transitions. I plus 1 comma, let's stay in the 5 region, or we can go in the 4 region. And dp I comma 4 is nothing but dp I plus 1 comma 4, because we can't now take any other elements. We will just go till I plus I becomes n. So we will just keep continuing forward. So these transitions we will have, and we can just take the maximum value. And you can see how we use the idea of sub problems to solve the main problem. We defined a sub problem like this, and then we use these two sub problems to find the answer for this sub problem, and which overall led us to finding the answer dp of I comma 0. So dp is quite a strong concept that we can use to solve problems. We can break our problem into smaller problems and then use these answer for these smaller problems to find the answer for the bigger problem. So these transitions when we can use. Now let's do the time complexity analysis. So time complexity of dp is O of number of states into average transition per state. So since we only have 2 or 3 transition per state, so the average transition would be 3 and the number of states would be n into 5. So our complexity would be O of 15n, which is O of n only, which will pass pretty easily in this problem. Also, we also need to solve this case where we will just swap a and b and rerun our dp, and that we will get the answer. So I'll show you guys the code for this. So first I take input a and b, and also n, and then this visited is for maintaining the states that I have already calculated the answer, and then answer 1 is dp 00, and then I swap A and B, and the answer 2 is DP00, and then our final answer is maximum of both of these. And now I'll show you guys the DP. So did I okay, I think I missed this transition while explaining. So also I can skip on the regions 3 and 5 and go straight to region 4 after region 2. That just means an array looks like this. Both of them ended at the same index, and then region 4 started. So yep, this transition, I think I missed it. Yes, I did not write it here, I forgot. So yes, you guys can check out the code. The transitions are just as I explained, and if I missed any transition while explaining, you guys will understand it just by just looking at the code. It's not very complicated. I explained it. So 3, then 2, and 2, 2. Okay, I don't think I missed any other transition other than this. So this is the transition that I missed, and rest of the transitions are same. And then this is for memoization. This is memoization, and this is the base case. So I must end with a region greater than 2. Only then the value is valid. Else I'll return a very small value to discard that case. And yep. So that was the solution for problem D. If you guys have any doubts, you can ask. So I think you guys don't have any doubts. So I'll move on to the next problem. So problem E, markers on a tree. This is the easy version of the problem. Here you only need to find f of s. For a tree T consisting of n labeled nodes labeled 1 through n, consider having two markers, marker A initially located at node 1 and marker B located at node n. In one move, you can move exactly one of the two markers from its current node to an adjacent node. A node is considered visited if there was at least one time instant where either marker was placed on the node. For a given subset S of the vertices, define f of s as the minimum moves required to make all the vertices in the set S visited such that the markers are back at the starting nodes. That is, marker A is back at node 1 and marker B is back at node n. The vertices not present in S may be visited or not visited. For example, for the empty set S or the set S equal to 1 comma n, f of s is always 0 because the empty set has no vertices to visit, and 1 and n are considered visited at the very start itself. You are given a tree consisting of n labeled nodes and a subset S of nodes. Find f of s. The tree is given in the form parent 2, parent 3 till parent n, such that there is an edge between the separate S given as a binary string. Explain this. So, and the constraints for this problem is n is given less than or equal to 5,000, and it is said that sum of n over all test cases does not exceed 5,000. So the overall time complexity expected would be O of n square. So problem E. Basically, in this problem, we have two markers. Initially at node 1 and at node n. So, and in one move, we can move either of the two markers. And what we need to do is find the minimum number of moves to visit each of the node given in the string S with at least one marker. Comma, in the end, the markers must return to their original location 1 and n. So that is the problem. Let's see the test cases. So the test cases are, first test case is just 1 and it would be visited in the starting only. 1 and 2 both would be visited in the starting only, so 0. Then the next test case, parent of 2 is 1, then parent of 3 is 2. This is the tree and each of the node is in the subset. So, and we have the marker here and the marker here. So obviously we'll just need 1 and then 2 moves so that each of the markers are at their original position and all of the nodes in the subset are visited. So the answer is 2 for this case. Then we have 2 is the parent of 1, 3 is the parent of 2, sorry, 2 is the parent of 3, 1 is the parent of 4, and 3 is the parent of 5. So this tree we have now. Then we have 2, 4 and 5 in the subset, 2, 4 and 5, and then we have markers here and marker here. So again, we can just do it like this. So we will need 4 moves. Moving this marker is quite unoptimal. So again, 4 would be the answer. Then the next test case. One is the parent of 2, 2 is the parent of 3, 1 is the parent of 4, 4 is the parent of 5 and 6, then 2 is the parent of 7. And the nodes in the subset are 1, 2, 3, 4 and 6. 3, 4 and 6. The markers are initially at M and M. So I think 1, 2, 3 and 4, 5, 6, 7 and 8. So 8 moves again. So the answer for this will be 8 simply. Now one thing we can say that it is inoptimal to visit the same node with both the markers. Obviously, right? Because if we had reached the node from any one of the markers, we can just whatever nodes that we visit from that node, we can just visit them from the first marker only. No need to bring the second marker there as well. So it is optimal to visit the same node with both the markers. So each of the node in subset must get visited by one marker only. So let's actually make a tree of our own, and let's analyze the situation that we have. So this is, let's say, our tree, and let's say we have this and we have this. Let's this also. So this is the tree, and the marker, let's say, is at this node and this node initially. And let's say that since we are visiting each node by just one marker at max, we won't be visiting the same node with both of the markers. So let's say that this is a part of subset and this is a part of subset and this is a part of subset, and these are the nodes that would be visited by this marker. So how will we visit them? So since this is a tree, right, and we need to go from here to here, so there is only one path. So we will have to go here, then we will have to come back, then we can go here, then we can go here, then we can go here, then again we will have to come back. So we can see that we need to retrace our path. Each edge would be traveled upon by each edge used to visit the nodes will be traveled upon twice. So we will follow this path, and what we need to do is we can see that the subtree of this node does not have any nodes that we need to visit, right? So we will not enter this subtree, and we see that again the subtree of this node is also not good, subtree of this node is also not required, subtree of this node is also not required. So we'll not go into those nodes, and the rest of the edges we will have to travel twice. So each edge used to visit the node will be traveled twice. So basically this will be the solution if there was only one marker. We can just go to each node, we can connect each node, and then we can remove all the remaining edges, and this would be our answer. Now since we are given two markers, right, so we need to use both of them to find the best possible answer, because if there was a marker here, then bringing this if there was a node in the subset here, then bringing this marker to this node would be unoptimal. We could have just done this. So what we will do is, since we have n square expected time complexity, right, so we can basically kind of brute force this from now on. So what we can do is, let's just take this tree again. How do I select this? Then I can copy this and I can paste this. Okay. Let me remove this. So what we can do is, we can divide the nodes into two parts. One part will be visited by this marker and one part will be visited by this marker, and we can do this for all the n possibilities. That would be O of n square solution. So what we can do is, since we need to find the part which will be reached from only this marker, right? So that can either be just this node, or we can take this node, or we can take this subtree, or we can take entire subtree. So basically we can take the subtrees of the ancestors of this node. Obviously, choosing a region like this is a very bad region, because to enter this region, to enter into these nodes, we will have to enter into this node, and keeping this node in the region of this node as well would be unoptimal for us. So let's divide this node. So let's divide this tree into two parts like this, so that each part will be only visited by one of the markers. So dividing it like this would be good, but dividing it like this is not good, because here if this marker has to go to this node, it will have to go to this node, but this node is in the region of this marker. So then that is not a good distribution. That is not what we want. We want a distribution like this and this. So this will ensure that this marker will check for all these nodes, and this marker will check for all these nodes, and then we can do this for every ancestor of this marker. So let's take, for example, let's say that we are checking for this ancestor. So what we can do, we can erase this node, and now we can calculate the number of moves required by this marker to reach all the nodes in this tree and reach all the nodes in this tree. Not all the nodes that were in the subset. If there were these two nodes, then this much. So now we would just have two problems, which are one marker problems, and we can find the answer for both. We can add the answer, and we can find the minima for every vertex, minima over all the ancestors of this node. So we can solve this problem like this. And so now let's focus on solving the problem for one marker. So that is very simple. We can just do it in one DFS. So let's say this is the marker and this is the tree, and the nodes we need to visit are this. So what we will do, we'll start the DFS and we will maintain two values, res, comma, what exact names did I give in the code? Okay, so answer and mark, we need to maintain these two variables for each node. What this will tell is marked will be the number of nodes in the subset that are in the subtree of the current node. So for a node, we will maintain these two values. So let's say for this node, mark will be equal to 1, because there is a node in its subtree that we need to visit, and answer is the number of moves that we need to make inside this subtree. So that is, so for this node, obviously answer will be equal to 1, because after coming to this node, we only need to make this move, and basically answer is the number of edges that we need to travel. So only this edge. And marked will be equal to 1, since there is only one edge that is marked inside this subtree. So if there are no marked edges, then we don't need this subtree and we will cut off it from here. So for this node again, we will have 1 and 2 answer, and there will be 2 marked nodes. So we will have to add this edge as well, since there are marked nodes inside the subtree. So we can follow this logic to find the answer for this subtree, main subtree. So I'll show you guys the code. So this is the DFS. I'll just start from showing this. So initially the answer will be 0, and then marked will be if the current node is marked or not. Then for each child, what we will do is we will just add the values for marked for each child, and answer also we will just add the value of whatever number of moves that we need to make for this child. So when we are calculating for this node, the number of moves we need to make in this subtree plus the number of moves we need to make in this subtree plus the number of moves we need to make in this subtree. Add all these, and now we are left with these 3 edges, right? So for them, we have this. So if there are marked edges in the subtree, then obviously we will have to traverse this edge as well, right? So whatever answer we did have, we will just increment it by 1, So this edge also is accounted for. So that way we'll count the total number of edges that we will need to visit, and since every edge will be visited twice, since we need to retrace our path back to root, so the total will be 2 into answer. So what we can do is first we will take input the graph adjacency list, then the string s, and initially let's just take our answer as 2 into n because 2 into n is all the nodes, and then we will start at the ancestors. So we will start first with this ancestor, then this, then this, then this. So what we will do is we will just erase this edge. So if we are talking about this ancestor, so we will erase this edge, and that will make these two different subtrees, and we will solve them separately. So we will erase that edge. So we will erase from node its parent, and from parent the node, and current will be the number of edges that we need to traverse. So one DFS will be from node 1 and another DFS will be from node n, and since they are the roots, they will not have any parents, and the answer will be 2 into cur, and then we will again add the edge that we deleted, and we will move up one step. So after we calculate from this ancestor, we will go to this ancestor, and then we will delete this edge, and again calculate the number of edges, and then 2 into number of edges. So this way we will calculate for each ancestor, and for the minimum for all of them would be our answer. So that is the solution for problem E. If you guys have any doubts, you can ask. Okay, so I don't think you guys have any doubts. So I'll end the meeting. Thank you.